Okay, a car drives off an 80-meter tall building at a speed of 38 meters per second, which is about 90 miles per hour, I suppose. How far from the building will the car hit the ground? Okay, so this is sort of what you would think of as a classical example of a two-dimensional projectile problem. The projectile being the car. The reason that it's two-dimensional is because although we start off with just one dimension with the car just moving in the horizontal axis, as it leaves the edge of the building, it's going to start to fall, which means that it's going to start moving in two dimensions, right? At that point, both in the horizontal axis and also in the vertical axis, or in the X and the Y simultaneously, right? And those two components, right, are going to produce a single trajectory that will look like sort of a diagonal line leading all the way down to the ground. And what we want to know is horizontally, right, how far is that point from the building, okay? So mathematically, right, like the math of doing this really is not that difficult as far as solving for the variables that you need, right, after you choose the right kinematic equation. Really, at the heart of doing these sorts of problems is just a need to really understand a couple simple concepts, right, about how objects fall and how they move in two dimensions simultaneously. Okay, so one thing that is really sort of at the foundation of this is that objects in a vacuum fall at the same rate. And you've probably discussed this at some point, either like a basic physics class or in a general science class, or you may have, you may have heard someone talking about this, right? About how like a feather in a bowling ball will fall at the same rate as long as you're in a vacuum and there's no air, okay? A baseball and a 747 jet, right, fall at the same rate as long as you are in a vacuum. The reason you start to see different falling behaviors for different densities and different weights, different surface areas, right, for different objects right, within an atmosphere is because now you're starting to deal with the relationship between an object and the friction caused by its movement through a fluid, in our case, the air, right? And then all of a sudden you have the air creating an upward force, right, which will be greater and greater and greater as there's more surface areas to sort of receive that force, right? And then that force will be resisted by the weight of the downward force of that object, right, which is greater, right, per unit surface area, the greater the density is, blah, 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 right? And so we start to see these different falling behaviors. But for the sake of teaching basic physics, what I want to do is just do this problem in sort of an imaginary environment where there is no air resistance. And this is what you'll usually find with a basic physics class. You take these classes and you have like frictionless tubes and massless strings and environments with no air resistance as cars fall through the air, okay? So that's what we'll do here. And we will just assume, right, that this car is going to fall, right, no different than any other object would fall, right, in a vacuum, which is why I left out the weight or the mass of the car itself. Another important thing to understand is that as this car moves through the air at all points in its trajectory, at all points during its journey through the air down to the ground, it's going to have both a horizontal and a vertical component, okay? So these components are perpendicular to one another. And what's important to understand about an acceleration that is perpendicular to a particular velocity is that acceleration cannot affect the magnitude of that velocity. Can't. Because no part of this acceleration downward is in the same axis as this velocity that is horizontal, okay? Now it can change the direction, right? A perpendicular acceleration can change the direction of a velocity, right? But it cannot add or subtract from, cannot add to or subtract from its magnitude, right? So as this thing moves, it's not going to be gravity that slows it down, right? In fact, if we're treating this environment as though it's a vacuum, the 38 meters per second that this car starts at is going to be exactly the velocity that it ends at as well in the horizontal axis, right? As per Newton's first law, unless a net force acts upon an object, right, its motion will stay its motion, its velocity will stay its velocity, whether it's 0 or 1,000,000 meters per second, right? It will stay that way until some sort of net force acts on it one way or another, okay? So given that no net force is acting on this, right, in the axis of the horizontal velocity itself, that horizontal velocity will remain constant throughout this entire process, okay? So really, our strategy for trying to determine how far it moves, right, will just be to first determine how many seconds it's actually in the air, right? How many seconds it's actually in this vertical axis. And then just sort of, common sense should tell us that it should end its journey in both the vertical and the horizontal axis at the same time, right? And then we can just use that time and the known horizontal velocity to see how far it goes horizontally. And that's what we'll do, okay? These components act independently of one another. That's sort of the point I'm trying to drive home here, right? So we can judge them independently, right, to determine what the sort of aggregate behavior of all of them will be. And you can kind of see, right, if you've taken any kind of basic trigonometry, that this diagonal path will basically be the hypotenuse of a right triangle created by the addition of these two vector components. So let me go back. Okay, so we're going to use one of the kinematic equations, right? In a basic physics class, you're usually given 4, right? The one that I'm going to use for this, right, a lot of times it's given to students in the in respect to the x-axis, right? The displacement in the x-axis. We're going to do it with respect to displacement in the y-axis. Okay, so here's the equation. It's going to be delta y, right, or the change in the y position, is going to be equal to the initial velocity in the y-axis multiplied by t, or the time, right, it takes this entire business to occur, plus 1/2 at squared. So 1/2 the acceleration of the object in the y-axis, okay, multiplied by the time squared. Okay, so just a couple things about this. First of all, we may know, right, that this object is moving 38 meters per second in the x-axis right before it leaves the building. But that does not imply anything about its speed in the y-axis. It's not moving vertically, right? It's not jumping up and down or doing anything in the vertical axis, okay? So its velocity, right, before it leaves this ledge, right, in the y-axis is 0, okay? So its initial velocity, as soon as it, before it starts to fall, right, as soon as it leaves the end of the building, it's just simply going to be 0. So this entire term, right, this term right here is 0, which means that this entire term right here, v naught y times t, is also just going to be 0, right? It doesn't matter what t is at that point. 0 times anything is 0. So we just cancel that out, okay? Now the delta here, the delta y, this is change, right? This Greek delta means change. And delta basically just means final minus initial. Right? So this is going to be the final y position, right, minus the initial y position. So sometimes you might define this start point as 0, right, in the vertical axis, right? And in the case of this particular problem, maybe then you would define the ground as -80, right? Since it's, it's 80 meters away from the 0 position in the y-axis, right? But going down, right? Going in the negative direction on that axis. You could also define the ground as 0, right? And define the start point as 80, right? Ultimately, as long as you keep your sign conventions consistent and you keep your terms consistent, you're going to get the same answer. But what I'm going to do is I'm going to define the ground basically as y equals 0. And I'm going to define the start point as y equals 80. So in that case, right, our final y position is going to be 0, the ground, right, minus our initial y position, which is going to be 80. So we're going to have a negative change in the position of y right, equal to negative 80, right, from start to end of this process, okay? And then one other thing, there really is no force acting on this object as it falls other than gravity, other than the gravity of the Earth. And we find that, in a vacuum, right, gravity accelerates all objects equally, right, at the same acceleration. And that is 9.8 meters per second squared, right, for Earth. That's specific to Earth, right? The acceleration due to gravity is unique to whatever point in the universe you happen to be, whatever gravitational reference frame you happen to be in, right? On Earth, it's 9.8 meters per second. And so that's what A is going to be, right? But and also in the negative direction, in the Y, okay? So let me erase this, let me rewrite this, and we will do our algebra in a way that allows us to solve for t, okay? So this goes away, and so we just end up with delta y equals 1/2 a in the y t squared, okay? So I don't really like this fraction here, right? I would prefer not to have fractions in my equation. So what I can do is I can just multiply both sides by 2. Okay. So multiplying both sides by 2. So this is sort of like multiplying it by 2 over 1. It's exactly what that is. So 2 basically cancels out. Okay. And then we just have to multiply the other side by 2 as well. Okay. So that gives us this. 2 delta y equals ay t squared. Okay. Now you can see here, right? You can basically just divide both sides by ay. No problem at all. And done. Okay. So now, 2 delta y over a in the y, right, equals t squared. If you want to get rid of that square, all we need to do is take the square root of both sides. Take the square root of this, right, and square root of t squared is simply t. And then there we go. There is our t. There is our equation for solving for time. And then now we can simply plug in some values to these variables. Okay, I don't know why I drew the equal sign like that. Using my PowerPoint as a whiteboard. Okay, so square root 2 times, remember, delta y is going to be our final, which is 0 meters, minus our initial, which is 80 meters. Okay, divided by negative 9.8 meters per second. Okay. And then let me just punch that into my calculator here and get ourselves an answer. So 2 times negative 80, okay, is negative 160, right, divided by negative 9.8, right, gives us positive 16.3265, okay, and then if I take the square root of that, I get about 4 seconds, right? 4.04, so we'll just try to be a little bit more precise here. And time equals 4.04 seconds, right? And you can see how this works out, right? Like the numerator is negative, right? Because we have a negative change. The acceleration, right, is also negative, right? And if that wasn't the case, we would have had a nonsensical answer because without imaginary numbers anyway, you can't really take the square root of a negative number. Okay? But yeah, this is the time. This is the amount of seconds that it's going to take for this car to go from the top of this very tall building to the ground. And the horizontal velocity of this car is going to be exactly what it started out as throughout that entire time. And so just intuitively, you can probably see that all you would need to do is just multiply these seconds, right, by how many meters the car moves horizontally for every one of those seconds, which is 38 meters. But even if you weren't thinking on those terms, like just by common sense, what do I need to do now? You can see just from the equation that this is also what you get, right? You get, let me take this away here, right? If I were, let me rewrite this equation with respect to x. If I were just going by the algebra, and you can use this equation for displacement in either axis, whatever axis you want, right? If I were using it with respect to displacement in the x, right, and I said, okay, well, delta x equals the initial velocity, right, in the x multiplied by t plus 1/2 at squared, okay? That's a in the x, right? Now, if that's what I was doing, or you would see that this entire thing would just cancel out completely, right? Because as we've mentioned, there is no change in velocity from one point to the next, right? At any span of distance, right? At any displacement in this process, right? In the horizontal axis, its velocity is constant throughout the entire thing, and the definition of a constant velocity is a zero acceleration. So acceleration would be zero in this case, right? Because the velocity simply isn't changing if we're doing this in a vacuum. And so this entire term would be zero, gone, right? And then all we're left with, as far as the horizontal displacement, as far as what that equals, is just this term right here, the initial velocity in the x multiplied by t, right? We have the initial velocity and now we have the t. So it makes sense that we would just use that to calculate our final answer, which is how far from this building the car will actually go, right? So 38 meters per second multiplied by 4.04 seconds. Put that in my calculator and we'll see how far from the building we should look for the wreckage of this car. 38 times 4.04 equals 153.5 meters. And that is our answer. That is our answer, all right, and I hope this made sense. And yeah, okay, thanks for watching.